Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska at Fairbanks. Today I want to talk about the solution to the second practice exam, problem 1. As before, I will discuss the solution to the problem in terms of the right answer and also in terms of the background that goes into the question that you should be thinking about in understanding the larger context for these questions. For question A, as the temperature of air increases, which of the following occurs? The correct answer is number 1, the saturation vapor pressure of the water increases. The reason for this is that the capacity of air to hold water increases as the temperature increases. And this comes back to the fact that water molecules are electrically sticky. They want to stick to each other. As the temperature increases, the molecules in a gas have a higher kinetic energy. They move with higher speeds and they ricochet more violently when they hit each other. And therefore, as the temperature increases, the ricocheting overcomes the stickiness and allows more molecules to exist in the vapor phase. Question B. As the temperature of a mass of humid air increases, which of the following occurs? The correct answer is 3. The relative humidity decreases. Remember, relative humidity is the ratio of the actual amount of water in the air to the capacity of the air to hold water. The capacity of the air to hold water increases with temperature, and therefore the relative humidity decreases even though the amount of water in the air has stayed constant. Question C. Which of the following is the most humid air? The answer is 3. Air at 50 degrees Fahrenheit with a dew point temperature of 22 degrees Fahrenheit and a relative humidity of 32%. We recall that relative humidity is a relative measure of humidity, and we see in this problem that the correct answer is the answer with the lowest relative humidity, but it is the answer with the highest dew point. The dew point of 22 degrees Fahrenheit says that the air has to be chilled to 22 degrees, at which point its relative humidity becomes 100% and condensation occurs or dew forms. Therefore, the dew point temperature is a measure of the vapor pressure in the air independent of the current temperature, and therefore it's an absolute measure of humidity. Question D. Which of the following statements about snow is incorrect? The answer is 1. Snow depth at a site is equivalent to the cumulative snowfall at that site. This is incorrect. Snow obviously changes on the ground. It changes its structure. It may even melt and go away. It may be blown away. And so the snow depth at a site is equivalent to the cumulative snowfall at that site is wrong. The snow depth does represent a cumulative record of fresh snow and remnants of past snowfalls, and the snow water equivalent varies with both snow type and as snow ages, and the snow water equivalent varies significantly in a snowpack. These are all things that you discovered when you investigated snow. E. In cold clouds, which of the following describes the precipitation process? The answer is 2. Ice particles grow at the expense of water droplets and fall through the cloud. Cold clouds are clouds that are cold enough for ice crystals to form. Many clouds are mixed phase clouds with water and ice present. We can have supercooled water at temperatures when we think ice should form. We can actually have supercooled water when we have small droplets of water. And so the problem speaks again to questions of vapor pressure. The saturation vapor pressure over ice is lower than the saturation vapor pressure over water, and this allows water vapor to migrate from the water droplets toward the ice crystals, letting the ice crystals grow. As particles grow, they fall through the atmosphere at higher speed, and therefore we get precipitation. F. The vertical profiles of temperature and dew point of a rising parcel of air and the ambient atmospheric temperature are plotted as 3 curves in figure 1A. I'm going to turn the page to 1A to discuss the figure while we discuss the problem. If we look at the figure at the top of the page, we have 3 curves. We have two red lines and a blue line. The first red line goes from point A at the top left corner to D to F. The second curve goes from B to C to F, and the third curve goes from C to E. And of course the overall plot here is a plot of altitude and temperature, altitude in the vertical and temperature along the bottom in Celsius. The altitude is given in both meters and kilometers. The three curves represent three different things, and so in identifying them, we start with which curve represents the ambient air temperature, and that has to be the curve ADF, the long dashed red curve with the solid red squares. The temperature of the air parcel is the short red dashed curve with the open circles, and that's the curve BCF. And the curve that represents the dew point of the air parcel is the blue curve with the open circles. That's the curve CE, the straight line. The reason I'm using the word curves here is because these profiles with height aren't always straight lines. In two cases, we have two straight lines coming together making the curve, and in one case we have just the curve being a straight line. How did I pull this out? How did I understand this? This speaks to the work that you've done in stability and vertical motion. Remember, at a given pressure, you know that a warm parcel will be less dense than a cold parcel. At a given pressure in the atmosphere, if I have warm air and cold air, the parcel of warm air will be less dense and lighter, and therefore it will be buoyant. So a parcel of air in the atmosphere can only rise if it's warmer than the air around it. And so in this case we see that the curve for the parcel is warmer than the air around it. Something had to disturb it initially that it would start moving. Remember, at the surface everything is at 35 degrees Celsius in terms of the ambient air and the parcel. If the parcel is somehow given a nudge, it then is free to move upward because it is cooling less quickly than the air around it, so it stays warmer than the air around it, and it rises from F to C to B, at which point it's as cold as the air around it and it stops rising. The dew point temperature is always equal to or less than the air temperature. So for the parcel, the dew point temperature curve is E to C. And so we're starting here with a dew point of 23 degrees Celsius, and the dew point falls at 2 degrees Celsius per 1,000 meters or per kilometer. And so as the parcel rises, you notice that its temperature is cooling, the dew point is cooling. Both the dew point temperature and the parcel temperature meet at C, at which point we have cooled enough that the temperature of the parcel is equal to its dew point temperature, and we have 100% relative humidity, and this is where the cloud will begin to form. So the cloud base is at point C, which is an altitude of 1,500 meters or 1.5 kilometers. The cloud continues to rise now with a relative humidity of 100% until it reaches the temperature of the ambient air at B, and so the cloud top in this case would be at 2,500 meters or 2.5 kilometers. If we go back and look at the air parcel temperature, F to C, we notice that the temperature is falling 10 degrees Celsius for every kilometer. And that's the dry adiabatic lapse rate. That's the temperature the parcel has to fall by as it rises through every kilometer, because remember, it's expanding as it rises, as it goes from surface pressure to lower pressures, and therefore it's pushing back the air around it, and it has to give up energy to push back the air around it, and this is seen as the fall in temperature. When we get to C, condensation is now occurring. We have release of latent heat. So we now have an energy source from the water in the cloud, and therefore we cool more slowly. And going from C to B, which is a height of 1 kilometer, we cool by 6 degrees from 20 degrees Celsius to 14 degrees Celsius. And so the parcel temperature decreases with height in the cloud at 6 degrees Celsius per kilometer or 6 degrees per 1,000 meters. The next question is, at what altitude would the cloud base be if the dew point temperature of the surface increased to 27 degrees Celsius? So if you think about it, if you slid the blue curve across And that's the way you would solve this graphically. If you didn't want to do all the math, you would just take the blue, put a ruler along the side of the blue curve and move it over so that the dew point temperature of the ground was 27 degrees Celsius. And I've actually done this for you. It's not required in the solution, but just to explain this to you very carefully, I've done that in the lower left panel where I've moved the blue curve over, and we can see how the curves now all change. In that situation, we see that when the dew point is 27 degrees Celsius, the parcel now cools to 25 degrees Celsius at 1,000 meters before the dew point becomes equal to the parcel temperature. So at higher dew points, the cloud reaches 100% relative humidity at a lower altitude, at 1,000 meters or at 1 kilometer. We also notice in this case that once condensation is occurring in the cloud cools more slowly than it did in the dry case, and therefore now the cloud can actually ascend higher in altitude before it reaches the temperature of the air around it. So in this particular case, at the higher surface dew point temperature, we find that the cloud bases are lower and the cloud tops are higher. So clouds change quite a bit if you change the amount of water present. The last question, based on this plot, if water did not have a latent heat of condensation, would cloud tops be higher or lower in general? And the answer is that cloud tops would be lower. If I look at the plot in the lower right, we see that going back to a dew point temperature of 23 degrees Celsius, the cloud base is at 1,500 meters as before, but now instead of having a kink in the curve, we continue cooling at 10 degrees per kilometer, and we see that we cool to the ambient air temperature now at a lower altitude, somewhere at about 1,800 meters. And so now we see that if there wasn't latent heat release, clouds would cool more quickly with height as they rise and therefore become less buoyant, lower in the atmosphere. So this gives you an idea of what goes into cloud dynamics as we talk about the temperature behavior of parcels of air in the atmosphere and the role of latent heat of condensation in the atmosphere. There's a more detailed description below that I lay out. These are extra comments on the question to guide your thinking. The other types of problems that we've looked at in this category are the formation of Chinooks, where again we see rising air and the role of condensation in changing temperatures and how that gives rise to Chinook winds, the warm winds that come down out of the mountains in the American West and in Alaska during the winter, the snow-eating winds that we've talked about in class. Question G. Briefly explain how a sling psychrometer measures humidity and why at a relative humidity of 100% there is no difference in the wet bulb and dry bulb temperatures. In your explanation, please note the role of ambient humidity, evaporation, and energy transfer. In a sling psychrometer, the dry bulb thermometer measures the air temperature and acts as a normal thermometer. The wet bulb thermometer is covered with some muslin with some water in it. The water in the muslin is going to try and evaporate into the air. In doing so, it's going to take energy out of the thermometer, cooling the thermometer, and evaporate into the air. The amount of evaporation in the air depends on the humidity of the air. If the air is very dry, a lot of evaporation can occur, and therefore there's a lot of energy transfer from the thermometer to the water, and therefore the wet bulb thermometer cools significantly. If there's a lot of humidity in the air, then there's not going to be much evaporation, and therefore there's going to be a small amount of energy transfer from the thermometer to the water, and therefore the wet bulb thermometer is only going to be slightly lower than the dry bulb thermometer. The difference between the dry bulb and wet bulb thermometer, called the wet bulb depression, increases as the humidity decreases. What happens at 100% relative humidity? At 100% relative humidity, for every molecule of water that evaporates into the air from the muslin, there's another molecule of water that condenses from the air back to the muslin because the air is saturated. For every little bit of energy, latent heat of evaporation that the thermometer loses, it gains a little bit of energy, latent heat of condensation for the water that comes back from the air to the muslin. So on balance, it doesn't lose any energy, and therefore as a result the temperature measured by the wet bulb thermometer is the same as the temperature measured by the dry bulb thermometer. Finally, the last question of problem 1. A colleague states that they expect the climate of California to become hotter and drier due to global warming and predicts drought conditions for the state. You disagree, saying that if the Pacific Ocean warms, the climate of California may become wetter. Explain your claim by referring to figure 1b that shows the current ocean surface temperatures, central land temperatures, and prevailing wind direction in California. The prevailing winds in California come from the west, from the Pacific, and we will see when we look at circulation of the atmosphere, generally winds come from the west for good reason associated with the Coriolis force. But anyway, the winds are coming out of the west. Maritime winds are generally at 100% humidity. These are air masses that form over the ocean. They have 100% humidity out over the warm Pacific. California has a cold coast. It's to do with the current that comes down from Alaska, the Alaskan current. It also has very important issues in terms of the productivity of the fisheries in California. We don't discuss that here, but we take away the fact that the waters off the coast of California are cold at about 14 degrees Celsius. Therefore, as the wind comes into California full of moisture and lowers its temperature, the relative humidity increases. It's at 100%. Immediately it has to form fog as it cools. Condensation is occurring. And therefore the winds lose their moisture as they reach the coast of California and then head on into central California, much drier, with a dew point temperature of 14 degrees Celsius in a climate where you can have a July afternoon temperature of 38 degrees Celsius, so very low humidities. In our climate changing scenario, if the ocean were to warm off the coast of California, then the dew point temperature of the air coming off the ocean into California would be higher. The air would be fundamentally more humid, and so we would have moister winds coming in over California, and therefore potentially the climate would be more humid. And if it's more humid and there's more potentially rain occurring, then it's possible that water, which requires a lot of energy to heat up, will lead to a reduction of the temperatures in California because a lot of the sunlight will be used energizing the water in cycles of evaporation and condensation. And so it's not a simple question what happens, just that the deserts should automatically become warmer in global warming. They may actually become something other than deserts because of global warming, because the water vapor situation changed. The access of water in the climate changed. As I say in my comments, it's not that this is the fundamental insight about climate that I have as your professor. It's just to draw you into the complexity of climate and use your skills that you understand about moisture in the atmosphere and relative humidity and dew point temperatures to argue a complex situation about the transport of water in the environment.